Now we're going to go ahead and find those moments by go ahead and taking those cross products. So we cross product of R cross Vn, where R is represented as R1, obviously in the radial direction, and 0, 0 in the other two directions. And Vn is the normal velocity, which is a radial velocity, and then the tangential velocity, and then 0 in the z direction. And so when we make this cross product, it's pretty obvious that the first element is going to just be 0, all those zeros multiplying each other. Second element is also going to be 0. Both terms are going to be multiplied by 0, R1, 0, and then 0 v sub n. So only the third element, the z element, is going to actually have a non-zero component, and that's going to be the R1 v sub t, and minus 0. So our cross product comes out to be 0, 0, R1 v t n for that one. Similarly, R2 cross V out is also going to be just 0, 0, and then R2 VT out. So those are our two cross products. We can then plug that into our formula for the sum of the moments. So the sum of the moments is going to equal, with the minus sign on the inlet, because that's the from the formula, VT in, and then, K, and then M dot in, and then plus R2 VT out, the plus sign, K, and then M dot out. So that's our sum of the moments. Of course, the mass dot in and the mass dot out, steady state operation of a pump, they have to be equal to each other. So M dot in equals M dot out. We're just going to call it M dot. So we can simplify this to just M naught equals M dot times R2 VT out minus R1 VT in, all times just K. Let's see if that looks okay. Okay, yeah, it looks fine. So then we're going to observe that for this system, well, for all systems, I guess the sum of the moments is going to equal the torque. So we can put this as a torque equation. So the torque for this pump is equal to M dot times R2 VT out minus R1 VT in, of course, all in that z direction. And we can rewrite M dot. We know that M dot is equal to rho times Q dot, so that's usually how you see that. So we'll put the torque is now equal to rho Q dot, volumetric flow rate, times R2 VT out minus R1 VT in, all times that K hat. Now this formula here, that has a name. That's Euler's turbine formula. So you can try to remember that one. So that's your torque formula. It allows you to calculate your torque based on these tangential velocities. Now, we don't really know those tangential velocities most of the time. It turns out that for the ideal pump, the ones we will model that VT at the inlet is equal to 0. So that's an idealization, not a bad one though. So that's the velocity flowing into a pump like this. The velocity going into the pump region, into the impeller region, is only traveling normal to these surfaces. There's no tangential velocity as the fluid enters this blade region. So that's a pretty good assumption. As the water comes out, however, the fluid comes out on the other end, it's definitely going to have some non-normal components as it gets spun by that spinning blade. So it's going to have so VT out will not be 0. VT out will not be 0 because it is going to have that kind of velocity imparted to it by that rotation. So, but generally this formula will simplify because VT in our idealized model, that will just go to 0. So all you need to do is define VT out in order to calculate the required torque for a system like this.